let me show you how to write a basic test bench. We're going to write a test bench for a full adder. Here's a full adder we wrote using behavioral design. So we're going to use this and write a test bench to verify this design. Right? Okay, so let's just briefly discuss what a test bench is. So you have the design. We usually call it design under test. Right? So we're going to verify this design and we're going to supply your inputs. Okay, this is called the stimuli. In the case of full adder, it's going to be A, B and C in, and you're going to get some outputs from the DUT. So sum and carry, right? So all this is going to be within another block called the test bench. So we're going to call it the module name full adder underscore BH. We're going to add a underscore TB to it, right? So if you see, this test bench does not have any inputs. There are no inputs, there are no outputs, right? So it's a self-contained module. Within the module, we generate these three values and we supply these three values into the DUT, and the DUT will give out sum and carry values, and we can either check them or just print it out or display it on a waveform, right? Okay, so we're going to do these two now for a simple test bench. We're going to display it on a waveform and also print it out on the transcript window. So to verify any design, you will need a test bench. So test bench usually will have the same name as the module name with an underscore TB. That's the convention. So let's also follow that and go ahead and write. So you will need the same definition. This definition you will need, and we're going to follow port connections by order. So you can remember this order: SC, AB and CN. Right? So let's go ahead. So this particular design, you will have it in a file. This file, let's call it fa underscore bh dot v, right? So it's the usual convention to have the same name as your module name, the file name as your module name, right? In another file that is called fa underscore bh underscore tb dot v, we're going to write the following code, the test bench code. So when you compile this test bench, this file, this Verilog file, the design file, will be automatically under this test bench file. No? Okay, so Verilog will automatically pick it up. Any simulator you use, it will automatically align itself under the test bench. Okay, so let's write. So module fa underscore bh underscore tb semicolon, no inputs, no outputs, right? We need some reg and wire, so we'll do that as we need them, right? Okay, so let's instantiate our full adder behavioral block into our test bench. So this is our full adder behavioral module name. So let's use that name, fa underscore bh, and let's give a instance name fa1, and I'm going to use my local ports to make connections to my full adder behavioral module. So I'm going to go with the same name. You can have any other name also, S, C, A, B and CN. Right. So we're going to introduce a new block that is called the initial block. So initial block is a behavioral block, but it's different from the always block. That initial block executes only once, and initial block cannot be synthesized. So these two things you can remember: only once and cannot synthesize. Right? So this is not for hardware definition. This is not for hardware design. This is only for test bench. For simulation we use initial block. Right? Okay. So let's say begin, because we're going to have multiple lines, and I'm going to introduce another keyword, that is $monitor. $monitor will monitor any of the signal list that we give inside, and will keep printing statements whenever any of the values change. So $monitor is like a print statement, but it's like it watches signals, and whenever the values change, it will continue to print a statement for us. So the syntax is like this: $monitor and open brackets and quotes, and we want to print simulation time. So we say time is equal to %d. So %d is where the actual value will be filled, and it will be time is equal to and the actual value. That is what we'll get at the output. And it's good to give a tab, so escape character, and T, that is to give a certain space. And the next value we want to watch is A is equal to %b. So time we want to watch in decimal, and A we want to watch in binary, right? And continue to write in the same line, /t, b is equal to %b, and then /t, cn is equal to %b, and after the inputs we'll continue to watch our outputs. /t, s is equal to %b, /t, c is equal to %b, and once you've given the list of all things you want to watch, close quotes, comma, and start giving the actual values, the local values. So for time it is $time. So this picks up the current time, simulation time, right? And then A, B, C, N, S, and C. Then close brackets, semicolon. All in a single line, right? Okay. So since we want $monitor to capture any change in any of these values, we give it as the first line in our initial block, right? So after this, we're going to change A, B, and C in, and whenever any of them change, we want $monitor to print them, right? Okay. So this happens at time 0. So in simulation, we follow a time step. So at time 0, because we have not incremented time, so at time 0 we've initialized $monitor. Now we're going to initialize our values. Say let's initialize A is equal to 0, B is equal to 0, and Cn is equal to 0, right? So at time 0, all your values A, B, Cn, all three of them are 0, right? Okay. So I'm going to increment time now. So we do it like this, hash, say 10. So this is 10 time units. So we'll define the time units as our first line before the module definition as using a compiler directive, tick time scale, and then you give the time unit, say for example 1 nanosecond, and you also give the precision. So precision, I want it to be 100 picoseconds. So whenever you say #10, #100, that will follow this nanoseconds. So that will be multiplied by this time unit that you give. So when I say #10, it means 10 nanoseconds. And picoseconds is for value resolution. So how minute you want the resolution to be, the time resolution to be. So that is in 100 picoseconds. I'm not interested in a resolution below this, right? So I'm okay with 100 picosecond resolution, right? So once I've defined my time units, I say after 10 time unit, I want to change something. So say, let me change A to 1, and then wait for another 10 time units, and then make B to 1, and then wait for another 10 time units, and then make Cn to 1. So I've kind of had now 4 different values. So here A, B, Cn is going to be in the same order. It's going to be 1, 0, 0. And after 10 time units, A, B, Cn is going to be 1, 1, 0. And after 10 time units, these are comments. These are not part of the code. Right, 1, 1, 1. So here it was, say, time was 0 nanoseconds. Here it was 10 nanoseconds. Here it was 20 nanoseconds. And here it was 30 nanoseconds. So after 10 time units, say I've tested my design for a few samples. So I want to stop. So I use another $ command called $stop. So you have several $ commands. We'll see some of them later. So these are some common commands that we often use. So when you know that you have reached the end of your simulation, you can give $stop to temporarily suspend your simulation, right? If you give $finish, you will exit simulation. But if you give $stop, you can suspend. And if you're using a waveform window, you can still view the waveform. So it won't come out of the waveform. And now we can close the initial block, the begin and end combination. And then we can end our module. Right? So let's fill in our reg and wire. So regs are all that comes on the left hand side inside your initial block. So that is A, B and Cn. And your outputs have to be wires. So S and C. Right? And that's it. So this is the simple test bench that you can write for testing your full adder. So any full adder designed using structural or data flow can be tested using the same test bench, provided you just change the name of the module here, and you can use the same test bench to test full adder written using any design style.